Okay, so welcome everybody to the second day of our summer short course on quantum physics for everyone. Last time we discussed some basic properties of light, and we hinted around that light might be behaving like particles, but we also know from our previous learning in quantum physics that light also acts like waves. In fact, even in classical physics, light acts like waves. Today, we have a really nice opportunity to see an experimental demonstration run live in the latter half of this 2-hour session. And this will be provided by qutools, and Henning Weier from Germany will be doing the demonstration. So let me go right into here. This just shows our schedule, as usual. Okay, so moving back to the summary of what we saw last time, we just talked about the fact that if I have a single atom and dim light is passing by it, it can scatter or emit light into these two detectors, which we label B and B prime. And we found that typically only one of these can click at a time if there's just one atom scattering light. Now, this statement is true for what we call linear optics, and that more or less defines linear optics. It's a case where light interacts very weakly with matter, such as a beam splitter. But we also know that in nonlinear optics, we can divide a photon, and we discussed this at the latter half of last session. Now, I introduced last session a classical analogy, which is called parametric process. And I would like to now, I know from the Flexi quiz that a number of you tried this experiment at home. That's great. I also tried it at home. I went to my garage and I got out whatever pieces of wire and tools and whatnot I could clamp together and make a little demo. So I'm going to now go into that demo, which I have set up right behind me. So I'm going to go into, well, if you're in speaker view, can you see my pendulum? I'll have to talk loudly because I'm away from my microphone. So Amy, can you hear me talking?
I can.
Okay, good. So here we have a pendulum, and you can see it's just oscillating. And there's the natural resonance frequency of this pendulum. The frequency doesn't depend on the amplitude, as Galileo figured out when he was 8 years old in a famous story. It all depends on the length of the string and the mass that's put on the end of it. So by the way, my string that I'm using is actually a bass guitar string. It's one of the old strings I discarded from my bass guitar. Okay, so there's the, and notice that if I make it shorter, the frequency increases. Okay, so I have to figure out what length I'm going to work with. I'm going to work with this length right here. Okay, so there it is. You see the frequency. Now I'm going to pull it up twice as fast. Every time I get to the end, I'm going to pull it up. And I'm pulling it up very gently. I'm not putting much force at all. I'm pulling very gently, but I'm pulling at twice the frequency of the oscillation. So there's your proof. I can even do the opposite. I can push it down at the ends, and I can stop it from oscillating if I'm really good at it. So I can amplify the oscillation or de-amplify the oscillation. So the main point of that is simply, if you vary the parameter of an oscillator at twice the frequency of the oscillator, you can put energy into that oscillator. So is that clear? Are there any questions about that? Well, I'm not hearing any commentary, so let's move on. It's a classical experiment based on just a single oscillator. Now, light is a harmonic oscillator, but it's not just one oscillator, it's an infinite number of oscillators. Every different frequency of light is a different oscillator. So in our experiment, the blue light that goes into a crystal acts like my hand going up and down at twice the frequency. And then that oscillates an electron, or many electrons, inside of the crystal. That's our Jamboard. Right, so I'm gonna move on here. And we talked about this also. Inside the crystal, the electron is confined to move on an arc. So if I oscillate the driving force at a frequency omega, but the electron can move on an arc only, then it oscillates at omega over 2, as I'll demonstrate with this little demonstration here. You see, the driving force went back and forth twice when the electron went up and down vertically just once. And that's actually what's happening inside the crystal. The electrons are kind of frozen onto little tracks where they have to move in arcs. That's an oversimplification, but so the blue light goes in, acts as the driving force at twice the frequency and generates red light at 1/2 the frequency, as shown in this energy level diagram here. Now, creation time, that refers to the quantum physics analogy. If the blue light is not too strong, then it's going to generate very weak light. But we know from Einstein and Planck that when you make light weaker and weaker, at some point it starts to be seen as individual photons. So that means that these photons are produced in pairs, for one thing, because you have to emit 2 of them to conserve energy. If you annihilate a photon that's blue with omega frequency omega, you have to produce 2 red photons to balance energy. And the geometry of the situation is such that this photon goes up here in the A path, which is called the herald, and this other photon goes in the B path, which is called the signal. So we know how to do those things. In fact, Henning will demonstrate that later. So here's the deal. We either get 0 photons in both paths, or we get 1 photon in both paths. And the creation time of these photons is uncontrolled. We have no control over that. It just happens whenever it feels like happening. So if we get a click on this herald detector, we know, if everything is set up correctly, that there should be 1 photon traveling in this direction. But the question is, how do we prove that? Let's say we're not confident of the theory, or we're not confident of our setup or our detectors. So we want to prove that there's 1 photon here. This is called a heralded photon because this is the herald detector. So what we do, we consider this blue box as a source of heralded photons. When there's a click here, there should be 1 photon coming out of this box. In fact, Henning has such a box. It's very nice. No, actually, in Henning's box, both detectors are outside of the box. Okay. In any case, we have 1 photon coming here. In order to prove this 1 photon, we have a 50-50 beam splitter, which half the time passes the photon to B prime, and the other half of the time passes to B, and we have a coincidence counter. So then the question is, how do we characterize the probabilities? So I hope everybody had a chance to read this slide if you weren't here in the last session in the latter half, but I did go over it, so let me go over it fairly quickly. So we have different events, which we call X, Y, and Z, or A, B, C, or whatever, and we have probabilities. And the most important formula is this one. If we want to know the probability that the sun will set and the moon will be visible, so there's an and here. We have to know the probability that the sun will set, which we call P of Y, and we have to multiply that by the probability that given the sun sets, the moon will be visible. that is rather common sense. In fact, the famous physicist Laplace wrote all these things down a couple of 100 years ago. And it's called the theory of probability. So we have P of X is a probability for event X to occur. P of X comma Y is the joint probability for events X and Y to occur together. And P of X vertical line Y is called the conditional probability that given Y has occurred, X will also occur. Okay, so here's our setup again. We want to measure the ratio. We call it G2, and it's equal to the ratio of these three probabilities, but conditioned on given the fact that A clicked. So given that A clicks, the probability that B and B prime will also click is this one. And the probability that B will click is this one, and the probability that B prime will click is this one. And this ratio is a useful quantity that we call G2. So here's the Jamboard question. What value should G2 have in this experiment? So I remember when you go to the Jamboard, look in the chat window and click on that Jamboard link. And I will do the same if I can remember how to get there. There I am. So not everybody is on there yet. I can see there's only about 12 people there. So everybody go to the chat window, click on the Jamboard link, and you should be seeing this page, which is page 1. I'm seeing more people are finding it. So good. So remember, the way I set these up is there's 4 pages for each question. And these are the blue questions. And then if your first name begins with A through F, start typing answers on this page. And then you can talk with the other people in your name group. And the question is over here, what value should G2 have in this experiment? That's easy, right? But what experimental flaws could make the value deviate from what it should be? So remember, G2 is, I should have shown the formula. G2 equals the probability that B and B prime will click divided by the probability that B will click and the probability of B, but that's given that A clicks. Okay, so what value should this quantity have, ideally, and what could make it deviate from that? So go ahead and find your page. Start typing what you think the answer is. And converse if that seems helpful. And the formula is given on page 1 in case it's not on your page. You can scroll to page 1 to remind yourself. Somebody post a reply. Okay, good. Some people are posting the answer to the first part, what value. Now try to answer the second part. So many people are giving the right answer that it should be ideally 0, but what could make that value greater than 0? So the answer that I liked the most from everybody was that some extra light could leak in. So over here, there could be a little dim light bulb, and extra photons could fly into here at the same time that our good photon is coming through, and then both B and B prime could click, and then G2 would be greater than 2. So here's the expression for G2 again. And now here's another Jamboard question. Re-express G2 in terms of these symbols. So I wrote this in a kind of a more intuitive way, just said given A, we have these probabilities. But now I want to rewrite G2 as a ratio involving these symbols. So please go back to the Jamboard. And now go to the next set of questions, which starts on page 5, 6, 7, and 8. Okay, let's go back to my keynote presentation. And a number of you did type the correct answer in, so good. So let's not spend too much more time on it, but here is the answer. And we simply use this notation that, given A, B prime and B will click, and that's divided by the product of these probabilities. Given A, B prime will click, and when you multiply two probabilities together, you can say and, given A, B will click. Okay. Moving right along. Now the question is how to determine the value of G2 from measurements. We think it should be close to 0 if things are working well. Well, Henning will show this, but I'd like to do a warm-up. So we pick a time interval called capital T. Maybe that's 1 second, maybe that's 10 seconds. And then we count the number of clicks at each detector, A and B. NA is the number of clicks at detector A, NB is at B, and NB prime is at B prime. But we can also ask that what the number of coincidence clicks at both A and B, that's coincidence, and at A and B prime, that's coincidence. And when we say coincidence, we have to specify how closely in time they should be to be a coincidence. It turns out that the electronics that Henning has can resolve the clicks down to about 100 nanoseconds. So if A and B both click within 100 nanoseconds, we call that a coincidence. Typically the time between clicks is much longer, like milliseconds or, tenth of a millisecond or so. Okay, so then we also have the case, the triple coincidence, the number of times within that observation interval that all 3 detectors clicked within the same 100 nanoseconds. Okay, so these are the numbers that we can, actually measure. And then we need to derive, using these probability formulas, a formula for G2. So again, I just summarized that here's the probability that both A and B click. It's given by this product. The probability that A and B prime both click is given by this product. I think that should be familiar to you now. Therefore, we write down what our formula was that we arrived at in the Jamboard. So now I can take each of these expressions, I can use these expressions and re-express them this way. So to get the numerator, which is the conditional probability, I take the triple coincidence probability and divide by the probability of A. That kind of removes this conditional A symbol here. And then I do the same thing. So I have divided by PA 3 times. Well, by simple fractions, you end up with a single PA at the top. So this is the basic formula. It's the ratio of these 4 probabilities multiplied together. Now we, let's see, we use this. Now we can replace these probabilities by these formulas which say the probability of A is the number of clicks at A divided by the total number of trials, which are short time intervals. So let's say each time interval is 100 nanoseconds, and there's some huge number of trials, millions, and only in a times we got clicks there. So that's a way of estimating probabilities from experimental data. Okay, so putting those together, we get this expression: G2 is equal to the ratio of the number of clicks at A multiplied by the number of triple coincidence events divided by the number of double coincidences between A and B and the number of double coincidences between A and B prime. This is a very nice formula. And well, Henning can measure that. It's great. Now I should make a comment, which I think I forgot to add to the slides. If quantum mechanics is true, or I should put it this way, if photons have a particle-like nature when they're detected, then as we know that this G2 should be close to 0. Okay, so we're going to try to verify that. We'll discuss later what would happen if we didn't believe photons were particles, but we believe photons were waves, or light was made of waves rather. Then what would be the value of G2? That's a question we'll discuss later. Okay, so here's a Zoom poll. So get out your calculator or your cell phone and use Google to calculate the number, or just calculate it on a piece of paper. And we will start the Zoom poll here, polling, launch poll. So everybody has to launch the poll, or rather the poll just popped up, I think, and you should.
Yeah. We all see the poll.
Good. I'll give you 60 seconds for this and see how many people can solve it in 60 seconds. I see some people posting the wrong answer. So if you're not really confident of your answer, please calculate that again. It's just simple numerical calculation. Okay, only 9 of 17 have voted, but that's maybe indicates that not everybody is actually a student or you're checking your email. No, I'm just kidding. Okay, I will stop the poll now. In the poll and share the results. And you can see most people said 0.04, and that is correct. So double check your calculation if you didn't get that. So here we are, 0.04. So good, that's the number that's pretty close to 0. It's about 4%. And as we said before, there could be some minor problems. There could be leakage of stray photons and whatnot, which makes this not strictly 0. So that's why I built this example here to mimic what it might look like in a real experiment. You never get exactly 0. Okay, now we have another issue. During the Jamboard, somebody mentioned a very interesting point. What if a photon hits the detector, but it does not produce a click? This actually does happen because it's only one photon. It's a very small amount of energy. That single photon has to jiggle electrons inside this detector strongly enough that they can be amplified and produce a voltage pulse. A voltage pulse might contain 1,000,000 electrons, but there's only one little photon hitting this detector. So it turns out that that does not always happen. Sometimes the photon's just absorbed and lost and there's no voltage pulse coming out. That's called the efficiency. So you call it eta, the Greek symbol, and it's the probability that if a photon hits, or given that a photon hits the detector, a voltage pulse will be generated. Typically that's about 80% or 0.8 for typical detectors. I think the ones that Henning uses are efficiency of about 10%. But we can buy other detectors that are more like 90% for more money. Okay. In fact, for $30,000, you can buy a detector that's made with superconductors, and it has an efficiency of 98%. So the Jamboard question is a little bit challenging. Write a formula for the mean number of coincidences at A and B. Well, this part's easy, actually. So let me define the notation. M in this red box is the number of photons that actually hit the detector. N is the number of clicks that are produced by this detector. So the relationship, of course, is that the number produced, N, equals the number hitting multiplied by the efficiency, and likewise for the other detectors. So now what's the formula for the mean number of coincidences at A and B? This is a little bit challenging. You have to think about that. So you have A and B, both of them have a chance to detect the photon or not detect the photon. So if you know how many photons are hitting A and you know how many are hitting B, what's the probability that you'll get a coincidence? So let's go to the Jamboard. Good. Okay, many people are converging on the right formula. And I'm going to go back to the keynote and discuss that. Here is the answer, because what it's equal to is eta times eta MAB, A and B. And that's because MAB is the number of photons that are simultaneously hitting A and B detectors in the 100 nanosecond time interval. But then we have to account for these probabilities twice because there are two events that we want to be successful. So we get this formula. Very good. I'm going to have to move on. So now we're building up the final answer for the detector efficiency. Write an expression for the mean number of triple coincidences. So given M is the number of triple photon events arriving at detectors, what is the number of triple coincidences that will actually be produced by these three detectors? So we have M, A, B, B prime. Let's go over to the Jamboard. I think this might be our last Jamboard. And we are going to express the result. Right, there's now three factors of eta because we need to have three successful events. So we have the number detected and multiplied by eta cubed. Okay, so see what I'm trying to do here is to make a connection between what's actually happening, with the photons and what Henning is going to be observing with his coincidence counter. M is the number of photons actually there, and N, or coincidences, and N is the number of successfully detected coincidences. And it has to do with eta cubed. Okay, let's move on. So now, this is the solution here. that we just wrote down. We summarized these solutions here. But now what I'm going to do is just skip through this because I don't want to take more time. G2, which we know is given by this ratio of the four n factors, which are the number of observed singles, doubles, and triples, is what we call those. Singles, doubles, triples. Now, but that's going to be related to the actual, those are the detected events. The M's are the actual photons arriving. But notice a magical thing happens. Here we have n cubed. Here we have, eta cubed, eta squared, eta squared. Boom, they cancel. So this means it's a very nice experiment. Even if your detector is only 10% efficient, if you collect data, you still get the correct value of G2. It's a very important point in measuring quantum optical signals.
There is a question in the chat about efficiencies.
Okay, I just opened up the chat. You also can all open it if you like. In real life, should each detector have different eta? Very nice question. In reality, they do. And I'll leave it as a homework problem or quiz problem to answer what happens if these etas are not all equal. Does it still cancel out perfectly? So for now, let's just assume that the etas are equal or they're similar enough that it doesn't matter. I just want to leave this as an open question for you to think about and not just give you the answer. But thank you for the question. So if the etas are equal, we can see the result is independent of efficiency. If the etas are almost equal, it's going to work as well. That's for sure. In fact, here is the question that was just posed. Very nice. Okay, now we're going to move over to Henning Weier, who is a scientist at the qutools company in Munich, Germany. And they have a very nice set of products that they build and sell, namely high performance photon detectors and electronics. They also make an educational kit, and we're very happy to have Henning here. He's going to do a demonstration. This is a picture of the apparatus that he'll show you. There's a photon pair source and this blue box. The photons come out in the two paths. And then these are optical fibers, these gray things. And the herald is A, it goes along here and goes over to this detector called A, or the detector is in the box, is inside this electronics box. We use the fibers to move the photons to the detectors, and we label those A, B, and B prime. And then here there's a beam splitter and a fiber beam splitter. So instead of using a piece of glass as a beam splitter, we put the photons in this path here into this fiber, and this splits this fiber path into two possible paths, this one and this one. Oh, by the way, these circles are just loops of fiber. They're not rings, they're just coiled up loops. So you go in, you loop around a couple of times, and you come out. So a given photon coming in here could either come out this path or it could come out this path. So that acts just like a beam splitter. I won't tell you what's inside this fiber beam splitter. That's a fun project, but that's not relevant to us right now. So there's a photograph with the cartoon colors on here, and Henning will walk you through this, I believe now. Is that right, Henning?
Yes, I'm ready.
Okay, then what I have to do is stop sharing. I have to enable multiple participants may share. So you may now share your screen, Henning.
Okay, thank you. Thank you, Professor Raymer. My name is Henning, as Professor Raymer already told you. I'm working for qutools. Oh, yeah, you can see me, I hope. Yes, I can also show you the slide here, and me just up in the little corner. So there's my email address. If you have any questions, you can also write them to me, especially concerning the experimental part. No, maybe not so much about the theory, but we'll see. So yeah, I'm happy to walk you through this, hopefully today. If I talk too fast, please let me know. This happens from time to time. and I will try to start this. I'm also trying to get some new technology working here, so we'll see whether this is always going to work in the first attempt. So I would first like to show you what this setup looks like in general. So I will now show you that probably a little bit more slowly, and with some other components with the slides in there. So let me check how I can do this, like that maybe. So I would just point at some of these things so that you also see that it's not a photograph. So I hope you see my finger moving around here. So,
yes, we do.
Great, thanks. So this is the whole setup basically. So we have the interesting part is really mostly this. So this is the optical setup, and I will go through this optical setup in a minute. And this is sort of the electronical part of it. So we basically have control of the laser that's in there somewhere, but we have control of the laser in here. And we have, that's also a pretty interesting part or important part of the whole setup, are these single photon detectors. So I will not go into detail today, at least what these single photon detectors are, but you can see that there are some fiber inputs here. And whenever a photon comes into these fibers here, with some probability, as we've already discussed, there will be some sort of electronical signal in, let's say, at the back of this, and then they are connected to some internal coincidence counter, and these count rates can be shown on the screen that I will show you a little bit later in more detail. And right, and this is, as I said, is the optical part of the setup. And I will open this lid a little bit later. This is where the real magic happens. But basically, these things are mirrors. So we have two mirrors, one here and one here. And we have fiber collimators here and here that basically just collect the photon pairs. So one for each arm of the photons. And then they go into these fibers and go into these single photon detectors here. So at the moment, I don't have this beam splitter yet. So we will first have a look at the source itself, because we will use this source a lot over the next 6 weeks or 5 weeks probably. So I will just give you a brief overview of this whole source. So let me try to zoom in a little bit on the, let's see how this works. So let me go. I hope you can see now. It's like a bird's eye view of the source, right? So my finger is here now, and I will remove this let's say this enclosure that's there for laser safety protection, like this. And now you can see the components. I will also show this slide here. These are the components that Professor Raymer already showed a little bit, right? You see the static ones on the right-hand side and the live one on the left-hand side. And I will try to use one of these screwdrivers here to show you what the important components are. Okay, this is going to be a little bit too bright maybe, but it's very light still outside here. So although it's already a little bit in the evening. So we have basically the laser, the blue, or it's close to UV, so it's about 400 nanometers wavelength laser here. There's a lens in front of it that you can't see, and there's another lens here that you can see, but it doesn't really matter. And the most interesting optical element we have here, so there's some mirrors here, so just to fold the path of the beam around the edge. And then the most interesting optical element we have here is this nonlinear crystal. It's called a bitter barium borate crystal, and this has a nonlinear coefficient that's sort of high enough to generate these photon pairs. So basically, you can forget about this and this optical element at the moment. This is not an optical element at all. It's just a pinhole, basically a bit of a hole, so that we don't get a lot of these stray photons from here. Right, so this is the most important element, and then these photon pairs are generated under an angle of something like 3 degrees to the pump beam. And so you see that we can sort of collimate or focus them. I will switch back to the previous one. Where you see, hopefully, let's see, where am I? Right, so you see these are then focused into these fibers basically, and then they go into the detectors. So if there are any questions at the moment, I will give you a brief chance maybe.
I don't see any questions.
That's good, great. So then I will put back the lid back on.
There is one question actually in the chat that just appeared.
Okay. There's one question. I can read the question. The question is, what does nonlinear actually refer to?
Yeah, that's a good question. So let me go back to where you see me a little bit. So I'm not sure I will be able to sufficiently answer this question. Maybe Professor Raymer has a bit of a better idea. So what it's officially, it's the nonlinear susceptibility of the material. So it basically means if you excite it with an external field, like with the blue light that we're using from the pump laser, then there's some chance that you generate, like Professor Raymer showed with his pendulum, there's some chance that you excite internally in this medium, let's say in this case, half the frequency, twice the frequency would also be a possibility. You can also shine in light from different colors, and you will get the sum and the difference frequency. So this is a general process that you always have whenever you have some sort of a nonlinear characteristics of your device, your medium, whatever. You will also see that in, for example, amplification, electronic amplification. You will also see that that you get the possibility of sum and difference frequency generations. And this is usually something you don't want a lot. So for example, if you have an amplifier, a hi-fi amplifier, you don't want that, right? You want the linear part as much as you can, and you don't want the nonlinear parts. But in this case, I mean, sometimes disadvantages turn out to be advantages. And in this case, we use this nonlinear effect to generate these photon pairs. And with this, I will give Professor Raymer a chance to express that maybe a little bit better.
Well, I'll just say very briefly that the word linear does not have to do with moving in a straight line or in a curve, even though I kind of showed a cartoon that way. It's an algebraic relationship. In a linear optical material, the electron's motion is linearly proportional to the force that's applied to it. So it's a direct proportionality. In a nonlinear material, the electron's amplitude of motion can be related to the square of the applied force or to the cube of the applied force. So it's not a linear relation in the mathematical sense.
Exactly, and in this case we use the second order, so the square part, but there's also like a third order and the fourth order thing, but we don't really use this in this case. So it's the second order that we use here. Right. Do you think that covers the question?
Yes.
Okay. Okay. So let's advance here a little bit. So basically, I hope we sort of shown the basic parts of this setup. Oh dear. I sometimes have trouble finding my mouse pointer, so bear with me sometimes. Right. So we basically showed the general parts of this. So I have closed this lid again. I will, for safety reasons, I will put the little screw here. Right. And now I could switch on the laser. This is something I will do from here. Right, let me just start this off a little faster here. Right, so, and now I will show this part of the screen that I usually, that we would see. Let me see whether you can't see this at the moment, but okay, so we will see this screen here. If I can find my mouse pointer again. Okay, I think that should be the one I'm looking for. Oh dear, almost. Bear with me. Now, right? You can see the screen of this. This is the screen that I'm looking at here when I look at this controller, and now you can also see it in this case. I have not switched on the laser yet, so let me tell you what these lines mean. You can. I hope that you can see my laser pointer as a little dot jumping around there in the center. Great, and right, and so these are basically the count rates that we see. So we have this blue line is the detector. Okay, I should start with the other one, but this is the detector B. The red curve is corresponding to the detector A, and the green one is corresponding to coincidences between detector A and B. And you will see this little number of multiplied by 10 here. This means that we multiply this by 10 so that there's not such a big difference, because Professor Raymer already told you that our efficiency is not perfect. So it's probably, yeah, well, maybe you can calculate this efficiency later, but we'll see that it's not perfect, and that's why this factor of 10 is here, just to make these lines a little bit closer to each other. Right, but as I said, we haven't switched on the laser yet, and you just see that this is like on an oscilloscope or something like that, where the most current values are always on the right-hand side. You see I hope you can see these numbers here.
Yes.
And okay, great. So, and now I will switch on the laser beam. So this is the pump laser that I'm switching on now. So before, that was just stray light from what's around in this room, basically. As I said, there's still the sun's still a little bit up, so we'll see a bit of stray light here. But now we can see that this red and blue beam has increased. I will switch it off and on again. All right, so this is what happens when I switch off the laser beam. And I can also show you, I hope, what happens if I block just part of the, oh dear, mouse pointer gone again. Here we are. Okay, now you see, you also see the live image of the whole setup on the right hand side. And I take just this gray piece of paper and I will block the left fiber coupler here. You see that the blue curve gets, you see that there's still a lot of light left here, but you see that this has decreased a little bit, and certainly the green curve has decreased a lot. And the same happens if I block the other beam. The red curve gets diminished a lot, and the green one too, right? So this is what happens when either of the beams get blocked. Okay, you also see that there's a bit of fluctuation on these lines. So there's some sort of statistics going on that's not completely stable. And this is, unfortunately or fortunately, I don't know, is completely normal. So what I can do, for example, I can increase let me just increase the integration time. So now it counts, before it has counted for 100 milliseconds for each data point. And now it's counting for 1 second per data point. So you see that the fluctuations have decreased a little, and that's also something that's rather normal. If you average over a longer time, you will see that the fluctuations get less. Okay. Right, so maybe one word or a few words I could say towards the this coincidence counter we've already discussed. I think that this coincidence basically means that two events happen in a very close to each other concerning time. So we have an event in channel A and an event in channel B, and if they're closer together than our coincidence time window, which is on the order of a little bit less than 100 nanoseconds, then we count this as a coincidence. If there's only one, then it'll be a single. If there's another one somewhere here, this will also be a single one, but they will not form a coincidence. Only if those two are close enough together, then they will form a coincidence, and we'll count this with this green curve or with these green. We can also show it as numbers, right? So we'll go to this picture from time to time. So we will show these as numbers now, because the time, the temporal fluctuations or temporal dependence doesn't really interest us very much. So these are the three numbers that are interesting so far, because we have only 2 detectors, and 2 detectors can form only one coincidence. Right. Okay, I think this is it for the time being, and I would now switch to the
one question.
Sorry. Okay, great.
One question. The question, Henning, is this is Mike Raymer, of course. So the green curve is derived directly from the blue and red curves in real time. Yes?
So they are strongly dependent on each other, I would say. So if you can't have coincidences if you don't have singles, right? So if you have lots of events in one channel and lots of events in the other channel, you don't necessarily have to have a lot of coincidences. For example, if I switch off the laser again, then we expect these photons to be completely uncorrelated, because there's no process that should make photon pairs now. But we still have a few coincidences, and we have much more singles, right? So they are dependent very strongly on each other, especially if I switch on the laser now. Now we have strongly correlated photons in time. So that's what we call these photon pairs. And that's why the coincidences have now increased much more than they would have if we would just have put in uncorrelated photons. And maybe I give Professor Raymer another chance to improve this answer.
Okay, yeah, so the answer to the question is no. If you know the red curve and the blue curve values, you cannot directly calculate the green one, because that's the coincidence rate. And as Henning just nicely explained, going back to the formulas that I gave, remember we had n parenthesis a comma b. That's the number of coincidences that occur both A and B. And that cannot be derived directly from just the number of events at A multiplied by the number of events at B, as we saw on the Jamboard. So I hope that clarifies.
Okay, so now let's switch over to this, to the different setup where we have this beam splitter in the path B. All right, so let me see how we do this and where my mouse is. Oh dear, it's just gone again. There we have it. Okay. Right. So now you see on the right-hand side, or on the right-hand side top, is a very a sketch basically. The bottom half of the right-hand side, you have the setup as we are going to build it now. So you can now watch me, hopefully not doing anything stupid. So, okay, so this, you cannot see that at the moment, but this is the device that Professor Raymer talked about before. This is this fiber beam splitter basically. So what you see is there's one input of a fiber here, and there are two output fibers here. So it's basically, this one is split up into two. And if you think that this is somehow very asymmetric, then you're completely correct. There's another fiber output somewhere in here that just hasn't been taken out to the outside world of this, because it's basically, it's impossible basically to make, or I wouldn't, maybe I shouldn't say impossible, but it's very difficult to build something where this is not symmetrical. And right, so now I have to find the right, so this is the input that, the input of the fiber beam splitter. I will use this B detector output, right? So the B output of the path from the down conversion source. And now I will connect that to this, right? Here, by the way, you have these fiber loops that Professor Raymer has talked about. And now I will, I have these two outputs of the fiber beam splitter, and I will connect those to the detector B and the detector B prime. Right. So, okay, now I will switch on this. You already see that it's not a perfect beam splitter, right? So you see, oh, you can't see that, sorry, but you will in a second. Okay, now you should see the screen again. So we still have the same number of singles in detector A. We now have about half of the singles in detector B and a little bit less than half of the singles in detector B prime. So it's not a 50-50 beam splitter, but rarely things are perfect in the experimental world. So this is what we have here. Now, we don't really care for these single events anyway. Okay, let's just briefly, maybe I can talk about threefold coincidences, but I think that's probably pretty self-explanatory now. So, so we have something like a twofold, let's put this in here. So we have something like a twofold coincidence when there's two events on different channels within the coincidence time window, but not a third one. And we have threefold coincidences when we have three events on three different channels within one coincidence time window. So this is what we call threefold coincidences, twofold coincidences. This would be single and this would be another single, right? So, and these are the ones that we need for this G2 function. So, right, so we have this, the G2 function on the upper right hand side here, or the, yeah, whatever you want to call it, the second order, the degree of second order coherence. There's lots of names for this. And so we have these threefold coincidences, right? These are the ones that you can see here. And we have a twofold coincidence, oh, we have the singles in detector A here. And we have twofold coincidences between channel A and B. These are these numbers. And we have twofold coincidences between channel A and B prime. It is this number. And I will now increase the integration time a little bit more, because you see this is a very small number. You don't see my mouse pointer here, but this is a very small number. And small numbers lead to lots of statistical errors. So I will just do 10 seconds integration time now. And now if we wanted, we could calculate the G2 function for the second order degree of coherence here in this case. So you see that there's still some fluctuations, but the fluctuations have become a lot lower relatively. So I can make this count once more, and then we could, if we wanted, calculate this G2 function, this G2 value. Should we do this on a Jamboard if you want, or should I just show it?
Dr. Raymer, you are muted.
Yes, what do you think, Amy? Should we do it on a Jamboard or should we just show the result?
I think it'd be nice to do it on the Jamboard, as long as we can take this image of the numbers of counts and put it somewhere on the Jamboard.
Okay, we are converging. Everybody likes 0.077. Yay, perfect. Thank you very much. So we can go back now to Henning.
So I just wanted to show you that I can also use this calculator thingy, and I got the same numbers here. So why is this not perfect? This can be a lot lower. So we have seen down to a few percent, like 1.5% or something like that. But we already said that whenever there's some sort of extra light or some extra clicks, this value will deteriorate. But to be honest, this value is still pretty good. We would call it a heralded single photon source when this G2 value is less than 0.5. So everything that you can do with what we would call a classical light source would have a G2 value of 1 or more. So whenever you go below 0.5, this is a bit of a convention, but then we say it's a heralded single photon source, or if it's not heralded, then it would be a real single photon source. So I think we can agree that this experiment has been successful, and we haven't done it for the first time, so I was quite hopeful that it will work. And I think, well, the result is that we have some sort of evidence is always a very strong word, but we have some sort of yeah, well, so sort of proof is even worse. So we have shown that there is some sort of a particle-like interaction or particle-like character of these photons that we might be able to call photons now. And with this murmuring, I will give back to Professor Raymer.
So this G2 quantity is a very famous quantity in quantum optics and quantum mechanics. As Henning said, if this is approximately 0, this is evidence of particle-like behavior, okay? Let's not call it particle behavior because we know that light is not made of particles. It's made of quantum fields or collections of photons, which are certainly not particles. However, what would happen if I measured G2 and I observed it to be in a certain experiment equal to 1? What would that mean? And how could I do that? It turns out that if I have a laser here, and I have a beam of light coming from my laser, and I put a beam splitter here, and it's a 50-50 beam splitter. And if I put my two detectors here, we like to call them B and B prime, and then I look at my coincidences here, what am I going to get for G2? Well, the property of a laser is that it essentially emits waves. So let's take a classical light picture of waves, or a classical wave picture of light. So a wave is something that goes like that, right? It oscillates in space and time. It travels with some wave velocity. And when a wave of a certain strength hits a beam splitter, it just generates two waves of a smaller amplitude because we've divided the wave into two parts. You could think of that as water waves, for example. And we could divide water waves by putting some kind of a barrier just below the water, right? So if you put a piece of wood just 6 inches below the water, and then you launch a water wave at it, some of the water wave will launch past it, but some of it will be reflected, and the amplitude will be divided by, into two parts. So now what happens if we have click detector? Well, this is a wave. A wave carries energy. So that means at any time, this detector could click. But that's independent of what's happening over here. And at any time here, the detector could click because there's energy in this wave and energy in this wave. Now you might say, well, let's just make, oh, so this means that G2 would not be zero, right? Because G2 of zero means that only one detector can click at the same time. As Henning showed, this is time. Now we have our small time interval. Now we have our two channels, B and B prime. And we can get clicks at any sort of random time. So we can get what are called accidental clicks. I mean, accidental coincidences within this interval. And we do get those, therefore G2 is not equal to zero. That's a property of light behaving like waves. And in fact, a laser does emit light that behaves very much like waves. It does not emit a single photon. There's no such thing as a laser that emits a single photon. And it's because it's a coherent field. And we know that lasers produce a coherent field. That's why you can observe nice wave interference by shining a laser at a diffraction grating or at two slits. So a laser emits a wave. Turns out that when you do this, G2, there was a question about the joints probabilities. It turns out in this case, the probability for B and B prime equals the product of B times probability for B prime. That's because these are independent events. And for independent events, you just multiply the two probabilities. Now, if you put that into the formula, you get G2 equals 1. And that's exactly what one observes in that experiment. So if G2 is 1, you say, oh, it's a wave-like, a light is wave-like. If G2 is close to 0, much less than 1, you say it's particle-like. And remember, these light sources are very different. To make G2 equals 0, we had to do this funny trick of photon splitting. And then we have the Herald detector, and then we have our single photon packet. And then we beam split that into two detectors. And now we can see G2 is closer to 0, right? So the point is that it depends on what kind of light source you make. And you have to work very hard to make these single photon light sources. But of course, a laser is cheap. For $2, you can buy a laser. But it does not make single photons, it makes waves. So this is a nice way to see the wave particle duality, or the fact that light sometimes behaves as waves, sometimes as particles. Are there questions about that? You could put questions in the chat window if you have a question. I do see question. The question is the beam splitter in this case nonlinear? The answer is no. The beam splitter is linear. This is a linear response beam splitter. So it's just a piece of glass with a little bit of thin coating of metal on one side, like sunglasses. And it does not have the ability to convert laser, photons from a laser into a pair of photons. What it does do is for each photon, you could say if there are photons here, it either passes it or reflects it. So because it's a linear beam splitter, the photons are indivisible. And because in a wave-like geometry, the photons can come at any time, they're all just independent here. They're all spread out or bunched together independently. They come through independently, they hit the detectors independently, then you can use this independent property or this independent formula for the joint probability. And that's why you get G2 equals to 1. In this case, this is a nonlinear a nonlinear, we don't call it a beam splitter, we call it a nonlinear crystal. It actually has to be a crystal to split one photon into two photons. And that's the nonlinear optics. And so in order for this to happen, you have to hit this crystal with very intense light because the process is very rare, very low probability. In fact, it turns out the probability to split a blue photon into two red photons is about 10 to the minus 9. Whereas here, the probability would be 0. You never split this laser photon into two photons because a metal beam splitter does not have that property. So, good question. Okay.
Professor?
Yes.
So what if you replace a beam splitter with a nonlinear crystal in the laser case?
Well, yes. The question is, what if I were to replace the beam splitter with a nonlinear crystal in this case? I can put that crystal here. And the answer is, now we are repeating the experiment that Henning just showed us. We have a laser, we have a nonlinear crystal, and now what happens is, what you have to be careful of is there's still, if this is blue, then you don't want to just detect blue photons like you would for the linear beam splitter. Now you want to detect red photons. So what you would do is you would put in filter here, which blocks blue photons, but passes red photons. And then you would put also a filter here, same type. Now, any blue photons that come here are blocked, and only when a blue photon is split into two red photons will you see a click here and a click here. And then we're reproducing Henning's experiment.